A certain building wall consists of 0.15 meter of concrete having thermal conductivity K is equal to 1.2 watt per meter per degree Celsius, 0.05 meter of fiberglass insulation having K is equal to 0.043 watt per meter degree Celsius, and 10 mm of gypsum board having K is equal to 0.05 watt per meter degree Celsius. The inside and outside convection coefficients are 10 and 40 watt per meter square degree Celsius respectively. The outside air temperature is -6 degrees Celsius and the inside temperature is 22 degrees Celsius. Calculate the overall heat transfer coefficient for the wall, R value, and the heat loss. So in the given problem, there is a concrete wall of a house, and inside of that wall is provided with a fiberglass insulation and then gypsum board to prevent heat loss. Generally, this kind of arrangement is provided in air conditioning room. So arrangement is like that. There is a concrete wall, outside is exposed to the environmental air, and inside is having fiberglass layer and then gypsum board layer. So the wall under consideration can be treated as a composite wall because it is made up of three different materials: concrete, fiberglass insulation, and then gypsum board. So in this problem, we are supposed to calculate overall heat transfer coefficient U, then R value, that is total thermal resistance value, and the heat loss, that is heat transfer from inside of the room to the outside, because inside room temperature is more than the outside temperature. This is typically the condition in winter season. So in order to solve the problem, first let us draw the schematic of this problem. So let us say the left hand side represent inside and right hand side represent outside. Now there is a concrete wall. So obviously thickness of the concrete wall will be more. Then it is provided with a fiberglass insulation, and finally it is provided with gypsum board. It is nothing but you can say plaster of Paris. In general language it is called as plaster of Paris. Now I can draw the 3D view of this composite wall so that you can have a better idea of area normal to heat flow and all these things, all other variables. So this is concrete wall then fiberglass insulation, and the third material is gypsum board. Let us say the thermal conductivity. So this is represented by material 1, 2, and 3. Let's say thermal conductivity of gypsum board is represented by K1, of fiberglass insulation K2, and that of concrete wall is K3. Let's say thickness is L1, L2, and L3 respectively. Now, this wall is separating basically two fluids. Inside of the room, of course, it is also having air, and outside of the room having air. So this wall is basically a wall separating hot and cold fluid. Hot fluid is on left hand side, that is inside of the room. Let me draw the hot fluid with the help of a fluid film. It is not visible. So as per our convention, fluid is represented by a thin fluid layer. The right hand side, left hand side represents in the red color room air. And let's say its convective heat transfer coefficient is H infinity I and temperature is T infinity I. And finally, the outside fluid is air. It is also represented by a thin fluid, a thin fluid film. And let's say it is having heat transfer coefficient, convective heat transfer coefficient H infinity O, and its temperature is T infinity O. From the problem statement, it is clear that the T infinity I is greater than T infinity O. So heat transfer will take place from left hand side at the rate of Q to the right hand side at the same rate. Now the fluid temperature will be represented by, let's say, at this point, let's say temperature of the gypsum board on the left hand side is T1. Temperature at the interface of gypsum and fiberglass insulation is T2. Temperature at the interface of fiberglass insulation and concrete wall is T3. And finally, temperature at the concrete wall right hand side face and cold fluid is T4, and temperature of the cold fluid is represented by T infinity O, and temperature of the hot fluid is represented by T infinity I. Now when heat transfer takes place from hot fluid to the cold fluid, by virtue of the convective thermal resistances, they hot fluid and different materials and cold fluid are going to offer thermal resistance, and hence temperature drop will take place. And for composite wall, the shape of the temperature profile is linear. So we will represent the temperature profile by a straight line. This way, this is nothing but temperature profile. And it is linear in nature, as we know from the heat conduction analysis of composite wall and plane wall. So we could represent all the detailed informations on this schematic diagram, and let's say area normal to heat flow is a meter square, which will be this area, and this will be same for all the materials. So we could represent different temperatures, thermal conductivity, thickness, convective heat transfer coefficients of hot and cold fluid, their temperatures and temperature profile. Now let us draw the equivalent electrical circuit of this arrangement. So the flow quantity will be Q, heat transfer rate. First, thermal resistance will be offered by hot fluid between temperature T infinity I and T1, and this will be convective thermal resistance represented by RT infinity I. Second, thermal resistance will be offered between temperature difference T1 and T2 by gypsum board. It will be conductive thermal resistance represented by RT1. Third, thermal resistance will be offered between temperature limit T2 and T3 by fiberglass insulation. Again, it will be conductive thermal resistance. Fourth, thermal resistance will be offered by concrete wall between temperatures T3 and T4. It will be again conductive thermal resistance represented by RT3. And final thermal resistance will be offered by cold air film, and it will be convective thermal resistance represented by RT infinity O. And finally heat will come out from the wall. So this is equivalent thermal resistance, equivalent electrical circuit. So see, there are three solid material layers and two fluid layers. So there will be total 5 thermal resistances into the path of the heat flow. Now second step is to enlist all the given things. It is whatever the parameters we have shown on the schematic, we will try to find out values of how many parameters are given in the problem statement. So as you can see here, a certain building wall consists of 0.15 meter of concrete. So value of L3 is given. .15 meter. Value of L2 and its thermal conductivity is 1.2 watt per meter degree Celsius. Then value of L2 is given as 0.05 and its case 0.03, that is fiberglass insulation thickness, and its thermal conductivity 0.043 watt per meter degree Celsius. And finally, the L1 value, that is thickness of the gypsum board, is given as 10 mm and 0.05 is thermal conductivity. So mm is not SI unit. We will immediately convert it into meter, and thermal conductivity of gypsum board K1 is 0.05. Watt per meter degree Celsius. Similarly, we have been given the inside and outside convective coefficients are 10 and 40 watt per meter square degree Celsius, and outside air temperature -6 and 22. So H infinity I is given as 10 watt per meter square degree Celsius, and H infinity O is given as 40 watt per meter square degree Celsius. T infinity I, that is inside room temperature, is given as 22 degrees Celsius, and T infinity O is given as -6 degrees Celsius. So this way we could enlist all the values of given parameters. Now no need to go through the problem again and again. The third step will be to write down all the assumptions involved. So the first very important assumption we will be taking as one-dimensional steady state heat transfer. I won't say it heat conduction because here heat transfer is taking place by combined mode, conduction as well as convection. So one-dimensional steady state heat transfer. The second assumption will be, since it is a composite wall, so there are two interfaces, and we know whenever there are interfaces, the fluid layer, the solid layers, if they are not in perfect contact, thermal resistance may come into picture. So we are going to neglect that thermal resistance because we don't have given any values in the problem statement. So no or negligible thermal contact resistance. We are totally neglecting thermal resistance and its effect. Third assumption will be, we are not considering any heat generation. The fourth assumption I am taking isotropic and homogeneous materials of individual layer. Individual layers of material. So as a consequence of this assumption, K1, K2, K3 will remain constant for the entire slab of the individual material. Then we have not been given the area normal to heat flow, so we will be assuming area normal to heat flow as unity. That means A is equal to 1 meter square. So we are basically going to calculate heat transfer rate per unit area, that is heat flux rate. So these are the 5 assumptions and they are more than enough. Then fourth point, enlist what is supposed to be found out. So first thing we are supposed to find out is overall heat transfer coefficient and symbolically it is represented by capital U. Second thing, we have to calculate total thermal resistance, that is RT. And third thing, I am supposed to calculate heat loss. Since area is not given, so I will be calculating heat flux, that is heat transfer rate per unit area. So schematic given assumptions find. And now let us do the detailed calculations. Now, in order to calculate all these parameters, first we have to assume the heat transfer rate through the hot fluid film layer, gypsum board, fiberglass insulation, concrete wall, and cold outside air is one-dimensional steady state condition. We are considering heat transfer only in one direction. So as a consequence of this, what will be the result? Heat transfer rate through all these 5 layers will be same. And depending upon the mode of heat transfer through each of the layer, we can write their heat transfer rate equation. So let us start writing heat transfer rate equation. So under steady state, one-dimensional heat transfer, what will be the consequence of this? The rate of heat transfer Q will be rate of heat transfer from inside of the fluid to the left face of the gypsum board will be equal to rate of heat transfer from left face of the gypsum board to the, the interface between gypsum board and fiberglass insulation will be equal to rate of heat transfer from interface of gypsum and fiberglass insulation to interface of fiberglass insulation and concrete wall will be equal to rate of heat transfer from concrete wall and fiberglass insulation to outer face of the concrete wall, and finally equal to the rate of heat transfer from outer face of the concrete wall to the outside air. So in this way, we can have 5 equation of rate of heat transfer. This will be by convection because heat transfer is taking place between fluid and surface. Again, this will be by convection, and these 3 rate of heat transfer will be by conduction. Now, since we are assuming one-dimensional heat transfer, so Fourier's law and Newton's law of cooling can be written depending upon the mode of heat transfer. So how can I write Qi dash 1? It is nothing but rate of heat transfer from hot fluid to the left face by convection. And Newton's law of cooling is for convection, HA delta T. So I can write in this fashion, H infinity I into area AI. So AI will be the fluid film area normal to the heat transfer. T infinity I minus T1. Q12 is the rate of heat transfer from left face of the gypsum board to the interface by conduction. So we can recall Fourier's law of heat conduction, Ka delta T over L. So K1A T1 minus T2 over L1. Similarly, for fiber insulation, K2A T2 minus T3, area of insulation glass will be same. Then for concrete wall, A3A T3 minus T4 over L3, and final rate of heat equation will be by convection from concrete wall to the cold air. Now here AIAO AI will be equal to AO will be equal to A, because we are going to consider only that area of the fluid film which is in contact with either left face or right face of the composite wall. So under such condition, area of the fluid film will be equal to area normal to heat flow. So that is the logic behind this. And since area is unknown to me, so I am going to calculate heat flux rate. So I will be taking area from each of this rate equation to calculate heat transfer rate per unit area. So these equations can be written as H infinity I T infinity I minus T1 is equal to A1A T1 minus T2 over L1 is equal to K2A T2 minus T3 over L2 is equal to A3, sorry, not A, there won't be any A, sorry, extremely sorry. Area I have taken common. And finally, H infinity O into T4 minus T infinity O. Now we can further rearrange this equation. So now hereinafter I am going to take a small q, that is heat flux rate. Now let us rearrange all these equations in the form of temperature difference and thermal resistance. So it can be written as 1 over H infinity I The second equation can be written as T1 over T2 L1 over K1 T2 minus T3 L2 over K2 T3 minus T4 L3 over K3 and finally T4 minus T infinity O will be equal to 1 over H infinity O. So we could represent all these heat rate equation in the form of temperature difference and thermal resistance. Okay, so I can also write it as T infinity I minus T1 over R T infinity I is equal to T1 minus T2 is equal to RT1 is equal to T2 minus T3 over RT2 is equal to T3 minus T4 over RT3 is equal to T4 minus T infinity O is equal to RT infinity O. Now, these are the heat rate equations, let's say represented by 1, 2, 3, 4 and equation number 5. These are the heat transfer rate equations through the individual layers of fluid and solid materials. Now, if I want to calculate the heat flux rate in terms of the inside fluid temperature, which is known to me, and outside fluid temperature, which is also known to me in the problem, how can I write Q? Q is equal to T infinity I minus T infinity O, and all these thermal resistances will get add up. Or T infinity I minus T infinity O is equal to summation of RT, isn't it? So if I want to calculate heat transfer rate, I must be able to calculate individual thermal resistances by fluid layers and solid materials. Similarly, what is the relationship between overall heat transfer coefficient and total thermal resistance? It is nothing but U into 1 over summation of RT. So in order to calculate heat transfer rate, in order to calculate total thermal resistance, in order to calculate overall heat transfer coefficient, we need to calculate individual thermal resistance. Okay. So in above equation, what is RT infinity? It is nothing but 1 over H infinity I. that is the convective thermal resistance offered by inside air. So 1 over the value of H infinity is, it is nothing but 10. And its unit will be degree Celsius per watt. Since I am taking per unit area, its unit will be meter square degree Celsius. Since unit area is considered here. So whenever we are considering unit area, the unit of thermal resistance will be meter square into degree Celsius per watt or meter square Kelvin per watt. General unit of total thermal resistance is Kelvin per watt. So you please keep this thing in mind. This is very important thing. RT1 will be L1 over K1 because we have considered unit area. L1 is 0.01 and the value of K1 is 0.05. So this will give me 1 over 5 meter square degree Celsius per watt. RT2 will be L2 over K2. The value of L2 is 0.05 and K2 is 0.043. This will give me 50 over 43 meter square degree Celsius per watt. RT3 will be L3 over K3. This can be 0.15 over 1.2. That is thermal resistance of concrete wall, and it will give me 1 over 8 meter square degree Celsius per watt. And the final thermal resistance, that is convective thermal resistance offered by the cold air, is RT infinity O 1 over H infinity O is equal to 1 over 40 meter square degree Celsius per watt. So in this way, we could calculate values of all 5 thermal resistances: RT infinity I, RT1, RT2, RT3 and RT infinity O. Now let us find out total thermal resistance. It is nothing but summation of RT, and it will be summation of 1 by 10 plus 1 by 5 plus 50 over 43 plus 1 over 8 plus 1 over 40. So the value of total thermal resistance comes out 1.613 meter square degree Celsius per watt. And this is one of our objective to find out the value. So I can write here, it is answer. Then comes U. U is nothing but 1 upon summation of RT. So it can be calculated as 1 over 1.613 The value of heat transfer coefficient U will be 0.619 watt per meter square degree Celsius. So this will be the answer number 1. This will be answer number 2. And finally, I am interested to calculate heat transfer rate or heat loss per unit area. T infinity I minus T infinity O over summation of RT. T infinity is 22 degrees Celsius. T infinity I is 22 degrees Celsius. T infinity O is minus 6 degrees Celsius. And the value of total thermal resistance is 1.613. Now see here, we need to balance the units. So this temperature difference is in degrees Celsius, and the unit of this total thermal resistance is meter square degrees Celsius per watt. This degree Celsius will get cancelled. This watt will go in the numerator. So Q will be 17.36 watt per meter square degree Celsius. So this way I could get the heat loss per unit area. Now, as per our procedure, let us sum up all the things. So I was supposed to calculate U. So U comes out 0.69 watt per meter degree Celsius. Then total thermal resistance RT, it comes out 1.613 meter square degree Celsius per watt. And finally, we were supposed to calculate heat loss per unit area, 17.36 watt per meter square. Watt per meter square. So this way, we have completed this problem. So what I want to convey, see the flow of problem solving. First, we could draw the schematic. We have represented all the important parameters into this schematic. We have drawn the electrical equivalent circuit. Then we have enlisted all the important given things. Then there are assumptions involved. Then we have also sum up what is to be found out, so that it is so that it will be bearing in our mind that these are the parameters we need to calculate. So what are the formula we are supposed to use? Then detailed calculations, step by step I have solved. I have not jumped out any steps, though it takes some time, but it avoids repetition. If you solve step by step, there are less chances of error. And finally, I could calculate all the things taking care of units. And finally, I have summed up the different parameters or values to be calculated.